Howdy and welcome. There are 4 handouts today. 2 of them have to do with the first programming assignment. One of them is the solution to the first homework set, and one of them are a set of lecture notes which will maybe start today and certainly start the next time. If you haven't gotten these handouts, please come pick them up. A couple of announcements. One is the second homework was to be due next Tuesday, but since we're running a little bit behind, we've decided to postpone that for half a week. So in fact, homework number 2 is now going to be due on Thursday, January 26th. Homework number 2 on chapter 3, due Thursday, January 26th, a week from today. Sorry? Because I'm getting behind. It's my fault, not your fault. I want to make sure that I've covered all the material in class before the homeworks are due. Reminder, tomorrow there will be a review session, 11 o'clock in the morning upstairs, Skilling 193. That review session will be on Verilog and will be broadcast for the SITN students on channel E1. And right after that, David will be having some extra office hours this week, one time only, 12 to 2 ERL 111. That's tomorrow, January 20th. Any questions, comments, remarks? Issues from last time? Okay. Last time, when we left, we started going over some measurements. After having discussed instruction set architectures in general, we were looking at measurements to help us justify the design of instruction sets and the decision of various features to include and not include. This one we had discussed, which clearly showed that it's important to have register addressing, use operand references in registers, that immediates are a big win, and that of all of the exotic addressing modes, the only ones that are a really big win are register indirect or displacement. Remember, register indirect is just displacement with a 0 displacement. And in fact, we'll see that the RISC architectures include this operand addressing mode and none of the others. Notice that this is application specific because SPICE, which is a heavily floating point array manipulation language, tends to use more of the scaled addressing mode and less of the register indirect addressing mode because it turns out to fit the kind of array accesses it does. But it's often the case that these kinds of exotic machine language features will fit only specific applications and are not a good thing to do in general. Well, if address displacement mode is so important, let's take a look at how big those address displacements are, how many bits we need to encode that information. If it turns out to be, in fact, the case that most of the address displacements are small, we can get by with allocating a small field in the instruction and have special escape cases for the rare cases when it's large. Well, in fact, it's not the case. Address displacements tend, at least in the range of 0 to 32K, tend to be fairly evenly distributed across the entire range. And the conclusion is that encoding, or trying to be very clever in the encoding of the displacements, is probably not a good idea. This information is, in fact, from the MIPS, where the displacement can't be any bigger than 15. It turns out that for displacement bigger than 15, where you have to use other instructions, the amount left over, the percentage varies from something like 5 to 25%. So making a choice like limiting it to 15, including those as part of the basic instruction encoding, and then paying a penalty for those 5 to 25% of the cases where you need to do something else because the displacement is bigger than 15, is probably a good idea. Let's look at immediates. In addition to displacement addressing, immediates turned out to be extremely popular. Where are they used? Well, it turns out that most of the immediates, or let me say it this way, most of the compare instructions wind up using immediates. So if you're designing an instruction set and not including a way to compare with immediates within the instruction, you're going to be giving up an awful lot of performance. It's less common for loads, but ALU ops, the percentage of immediates used there is in the 50 to 60% range. So it's certainly worthwhile including that as part of your instruction set design. Now we can ask the same question about displacements, which is, of the immediate values, which are the ones that tend to be predominantly used? Can we try to be clever about the encoding of immediates? And here, in fact, we get somewhat of a different answer. If you look at this data, which is from the VAX, it turns out that most of the immediate fields are relatively small. 8 bits or so will encompass probably greater than 50% of all of the immediate fields. Certainly 16 bits gets a good chunk of them. So this is a place where it may make sense to be clever about the encoding so that small immediates are kept in the shortest, most efficient possible representation, and longer immediates have to be done in some other way. You might be led to conclude from this that 0 as an immediate value is in fact not very common, and that's not the case. It turns out that the VAX has various special forms of instructions to implicitly use 0 as an operand, like compare with 0 and load 0, which is to say clear a register, because they knew in advance from other measurements and from seat of the pants reasoning that immediate field of 0 would be very popular. So they, in fact, even did it better than a small encoding. They implicitly encoded it by making the opcode imply that the operand is 0.
Question?
Yeah.
It seems very odd that there's a peak there at 20. What's do you have an explanation for that?
I don't have an explanation for that, actually. And 2 out of the 3 programs peak at that point, and one of them dips at that point slightly. And I don't know what the reason for that is. 2 to the 20th is 1,000,000. I don't know. Can anybody think of a reason why numbers at about that size would be important? It may have to do with the size of an address, and maybe that immediate field is an address rather than a constant for arithmetic. I don't know. These measurements always lead to questions like that. You see strange behavior of programs, and it's often very difficult to try to figure out what it is that's causing that to happen. It often turns out to be the case that in some inner loop of a program which dominates its execution, something strange is being done. Some instruction is being used in an unusual way. And often the only way you can figure out what's going on is to go back to the programs that were executed and look in detail at the instruction sequences they execute.
Can I ask a question about something from the book? The book is talking about immediate and literals, and I'm not catching what the distinction between those two is.
An immediate and a literal is basically the same thing. Now, if you're talking about VAX uses literal and immediate in slightly different ways, which we'll see later. But a literal is basically a very short immediate. But in my terminology, a literal field and an immediate field mean the same thing. They're constant parts of the instruction that represent operands.
You know, I was just confused because the book appears to be treating them as distinct things.
Okay, I'll take a look at that in the book and see if I can understand what they're doing and report back to you. Another thing to look at is that many of the more complex instructions handle various different sizes of data, byte, half word, word, and double word. Which of them, in fact, get used? Well, as you can see from this, predominantly it's word data. Double word data is used primarily for floating point, double word floating point arithmetic, which is why it shows up in SPICE instead of word arithmetic. And you might conclude from this, as did the designers of the DEC Alpha, that including instructions for doing explicit byte and half word manipulation may not be a good idea, because it's used infrequently. You can fake it by using word accesses and doing masking or various kinds of other multiple instruction operations. Let's look now at briefly at branch instructions and see what data we have to indicate how they're used. There are basically 4 or really 3 types of branches. There are conditional branches, which in fact wind up being 73% of the time that branch instructions are used. Unconditional branch instructions, which I prefer, and I think the textbook does too, prefer to call jumps, where the decision about whether to jump or not is known at compile time. It's an unconditional branch. And this is rather unfortunate because it turns out that the branch which is difficult to implement and make go quickly is the conditional branch, and the one that is a no-brainer that's easy to do is the unconditional jump. But that's life. Computers spend a lot of their time making decisions. Procedure calls and returns are done about 13% of the time. So important, but not up there with conditional branches. Now, there are several different ways to specify the destination address in a branch, or for that matter, a call. One is that you can use any of the addressing modes that we talked about before for data instructions. And in fact, the addressing mode specifies eventually an absolute address in the machine to jump to. That kind of thing is required for procedure return because the return value is not known at compile time and is not relative to the instructions being executed. The other way to specify destination addresses is to specify an address as the difference between where you're currently executing and where you would like to go, which is the PC relative mode. Remember, we talked about some of the computers having addressing modes which allow you to use the program counter as a general purpose register. So a free way to get PC relative addressing is simply to specify the PC as the register in the indirect addressing mode. A couple of advantages to that. One is that it can tend to use fewer instruction bits because, as we'll see in a second, lots of branches branch to the vicinity of where you're currently executing. So if you're specifying the branch destination address relative to the current location, then you can use fewer bits to encode that information. The other thing that is an advantage often is that specifying a destination address as relative to the program counter means that it's independent of where the program happens to be located. If you take that program or program fragment and relocate it somewhere else in memory, you don't have to do anything to change the branch instructions because they all are relative to where the branch instruction was. That turns out to be handy for linkers and loaders and various kinds of relocation considerations. Now, what is it that conditional branches use to determine whether or not they should branch? What are the preceding compares like? Well, it turns out that most of them are very simple comparisons. 79 or 80% of them are simple equality or not equality operations, and a very smaller number of them, 20% that remain, are complex comparisons that require an ALU operation, that require you to compare or to subtract two different numbers. We'll see later on that this turns out to be a very convenient thing to do, because if the comparison is simple, then you can wind up doing that comparison much earlier in the execution of the instruction than if the comparison is a more complex one. And in the RISC-like processor that we'll look in detail, we use this to great advantage. We saw from before that compares with immediates are the dominant case, 86%. And in fact, of those 86%, 83% of them are just compares to 0. So if you want to take advantage of that optimization, you should include an instruction in your instruction set that branches based on whether a value in a register is 0 or not 0, and not try to do a comparison with a second register. The next question, like having looked at displacements and immediate fields, is what does the branch distance look like? How far do branches typically go when they go somewhere? Well, this shows, for, again, a MIPS-like RISC processor, how many bits are needed to specify how far away the destination is from the currently executing instruction. And you see that 8 bits allows you to specify the vast majority of branch destinations. Why is that? Well, a lot of them are short backward branches for small inner loops. A lot of them are short forward branches for if-then-else kinds of constructions where the body of the then clause or the body of the else clause is relatively small. So clearly choosing an encoding for your instruction that allows you to specify a small number of bits is an efficient encoding to use. Note something else, that we're counting here not the distance in bytes between the current instruction and the destination instruction. We're counting how many instructions away to branch. it turns out that that's an advantage for RISC-like architectures, because in a RISC-like architecture where all instructions are 32 bits wide, you don't really need to specify the byte address of that instruction. All you need to specify is the word address of that instruction. So in fact, the low order 2 bits of every destination address is always 0 and doesn't have to be encoded in the instruction. So for a RISC-like machine, you get an advantage of 2 extra bits. You don't need a full byte address, as I said. This is a particular advantage for RISC machines because compared to the CISC machines where instruction lengths are variable, the RISC machines tend to generate more instructions. So the branch distances are typically somewhat longer. In fact, though, unless they generate 4 times as many instructions, you've already gained a factor of 4 in the amount of bits you need to encode the distance because they're aligned on word boundaries. The CISC instructions, there tend to be fewer instructions generated for a complex instruction set architecture, but there, in fact, you have to use an entire address, including a byte specifier at the end. The address of the target has to go down to the byte level rather than the word level. So you, in a sense, waste the extra fact that the instructions are more compact by having to specify more bits to indicate what the target is. These are the kinds of measurements that people, at least in the last 10 or 15 years, have been using to aid in the design of computer instruction sets. It's actually kind of interesting that before 15 or so years ago, designing instruction sets was very much a seat-of-the-pants kind of operation. There were very few places that you could go to look up statistics on how instruction sets are actually being used. And there are examples where people simply made the wrong decision by not knowing what the common operations were and what things ought to be efficiently encoded and what things mattered and what things didn't. Now there are books like a book that Mike Flynn has written and others that Hennessy, in fact the textbook that we're using, has lots of information that computer designers can go to try to make those decisions in a more quantitative way. What I'd like to talk about now is a little bit about compilers and how compilers influence the design of computer architecture, instruction set architectures, and how compiler optimization is important in the design of those instruction sets. Most programming now is done in high-level languages. That certainly wasn't always the case. In fact, it used to be the sort of badge of courage of a programmer was that he could get at least a factor of 2 or 3 more efficient code by hand coding in assembly language than writing in a higher level language like C. The number of diehards who believe that is beginning to decrease. And in fact, the design of the instruction set these days is such that it becomes easier for the compiler and more difficult for the assembly language programmer to get high performance out of the instruction set. So increasingly, the design of the compiler has as much to do with the performance of a computer as the design of the instruction set itself. That being the case, it's important to design the instruction sets to make it as easy as possible for people to write an optimizing compiler. What I'd like to do, let's skip over some of these details. What I'd like to do is to go right into an example of the machine language generated by a compiler in 2 different cases for a very simple loop written in C language so that you can get a feel for the kinds of optimizations that compilers typically do. This is not a compiler course, and if you're interested more in the techniques used for compilers to actually generate this code, then take one of the computer science compilation courses and compiler writing courses, and they're really quite fascinating. This is a trivial loop. It's a loop in C which basically adds to each element of an array B a variable C, which has been defined to have the value 10 outside the loop, and assigns the modified array to A. So the body of the loop is A sub I equals B sub I plus C. Let's take a look for a typical RISC machine for how that code might be generated if you ask the compiler to do no optimization whatsoever. Now, I realize that we haven't defined what this machine does, but that's okay. It's fairly generic, and you ought to be able to understand a sequence of instructions like this, even if I don't tell you that it's a MIPS processor, or something like a MIPS processor. So what happens first? C equals 10. This is a load immediate instruction that loads into register 14, a constant 10, stores the value of register 14. This is a machine that has 32 registers in memory location C. Notice this is, in fact, one of the memory direct addressing modes that we saw. Now it begins the initialization for the loop, so it stores register 0. Now this is a machine like the MIPS, in fact, where register 0 is defined always to contain the value 0 into a memory location, and in fact that memory location is an offset from the stack pointer, 4 of SP. So that has the effect of assigning 0 to I. Here's a question for you. Why is it that when I assign 10 to C, it stored it in a location using an absolute memory address, and when I have stored a value to I, it stored it into a location which is relative to the stack pointer? Anybody know why that is?
C's global and I is local.
Exactly. C was declared outside the body of the procedure, so is in fact a global variable, as are A and B, and I is a local variable which got dynamically allocated on the stack when that procedure was entered, and is therefore has to be addressed relative to the stack. In fact, I suppressed the instructions in this example that actually do the allocation, deallocation of local variable. So the fact that this is 4 is a byproduct of the style of dynamic allocation that was done by this compiler. So now we need to execute A equals B plus C. This is the loop. This is the target label for the loop. This is the branch that eventually gets there. And this code is straightforward and dumb. It loads a word into register 14 based on the offset of 4 from the stack pointer. Well, that happens to be I. Now, since I is a scalar index and references an array whose elements are 4 bytes wide, it needs to multiply I by 4 in order to get the offset into the array. So value of I times 4, store that on a temporary register 15. Now it needs to load B sub I. So it loads B. This instruction contains the base address of B as an immediate field in the instruction, and then adds to it the contents of register 15 as the offset within that array. So it loads B sub I, stores it in register 24. Now it loads into register 25C, and then it adds register 24, which is B sub I, with register 25 containing C. The result it stores in register 8. This is a RISC processor where ALU operations all take 3 operands, 2 source operands and a destination operand. The destination operand could have been the same as one of the source operands, but in fact, in this case, turns out not to be. So now we have the result of V sub I plus C in register 8. We need to calculate the place to store it. So again, load I into register 16, multiply I by 4. A sub 17, 17 remember now contains I sub 4, is the destination address, the place where in A sub I the result should be stored. So it does a store word of 8, the result of the addition, into A sub I. So now we've done the body of the loop, and we need to do the increment and test part of the loop. So we load into register 9, current value of I. We add to register 9 a constant 1, immediate field in the instruction, store that in register 10. Store back the result of I plus 1 into the memory location for I, and now do a test of I against a constant 100, and if it's less than, branch back to the loop at the target address, which is 33. 33 is not a register number. This is the location representing that instruction. This is fairly dumb code, and I'm sure you could all figure out ways to make it better. Obviously, it's been doing the same operation multiple times. It's been loading I multiple times. It's been multiplying I by 4 multiple times. Not necessary to do that. In fact, it's not even necessary to use I. One of the kinds of optimizations that the compiler itself will do is to suppress the use of I whatsoever, and we'll see in a second how that goes. But this kind of dumb compilation takes about 12 instructions per loop. In fact, it actually takes, on a MIPS machine, 13 instructions per loop, because this kind of instruction is an assembler pseudo-op. You really can't write an instruction which contains both a memory location, or even an offset from the PC to another location, and a constant as well. And in fact, what this instruction generates is two instructions that says set less than from some register, which the assembler or the compiler has to invent, based on whether current value of register 10 is less than or equal to 100, and then branch less than, I shouldn't use that mnemonic, but some kind of a branch instruction which tests register R. Let's say a branch if not equal to 0. If R is set to 0 or 1 based on whether or not register 10 is less than 100, then branch if register R is not equal to 0 to loc. So in fact, this is not really a machine level instruction. It's an assembler pseudo operation representing these two instructions. We'll see more of that when we go into one of the RISC-like machine instruction set architectures in detail. So this really takes 13 instructions per loop. Can we do better? Well, in fact, not only can we do better, but the compiler can do better. And this is an example of compiler-optimized code to do the same loop. Starts off the same way, loads into register 14 at 10, stores it in C. And now it starts the loop initialization. And in fact, notice that what it's doing here has nothing to do with the variable I at all. It's decided to ignore the variable I, to remove the induction variable, and instead to convert subscripted notation into pointer notation. And what it's doing is defining three pointers. LA is a load address, and if this is array A, it starts out with register 3 pointing to the beginning of array A. Similarly for array B, it starts out with register 4 pointing to the beginning of B, and then points register 6 to just past the end of B, B plus 400. And now what it can do, instead of using subscript arithmetic and having to do all these multiply by 4s and fancy addressing modes, it can instead treat these registers as pointers that advance down the array. So in fact, that's what it does. It loads from the location pointed to by register 4, which is the first word of B, the value into register 14. It now does an add to that of 10. Now notice it didn't bother to fetch the global variable C because it recognized that C has not changed within these instructions, and the constant C can be propagated into this instruction. So it fetches B sub I, adds to it 10, stores B sub I into, stores the sum of B sub I plus C into A sub I, which is the location to which register 3 is currently pointing. Now all it needs to do is advance the pointers. It advances register 3 by 4, advances register 4 by 4, and then compares to see whether register 4 has yet run into the end pointer that it had so conveniently pre-computed, sitting just past the end of B. And so it says branch if register 4 is less than register 6 to the beginning of the loop. Notice that this is an instruction that doesn't have to be expanded into two separate instructions because it contains simply two register designators and an offset to the next instruction. This is a pretty clever compiler. This is close to the state of the art for this kind of compiler given no other information. And we've decreased 12, or actually 13 instructions to 1, 2, 3, 4, 5, 6 instructions. Executes a lot faster. You're going to get in the homework to take a look to see whether in fact you can squeeze an extra instruction out of this loop and do even better. And then compare the optimized code that you can write for a RISC machine like this to optimized code that you might by hand be able to write for some of the other instruction set architectures.
Question?
Yeah.
Why doesn't that require SLTU and then a branch? And
the difference is that here you're comparing two registers, comparing one register to another. And the other instruction, the SLT, compared a register to an immediate field, which is much larger. And the design of this instruction set is such that you can only contain one large thing in each instruction, either an immediate field or it's the offset to the target instruction. So that's why in this case you can fit it in one instruction, in the other case you can't. When we actually get into the details of the RISC-like processor, you'll see in terms of the instruction fields how that works out. Any other questions? Now, what's the effect of doing this kind of optimization? Well, it makes the program run faster, but in what sense? Well, it decreases the total instruction count, decreases the number of memory references, and in general decreases the number of ALU operations. All those are wonderful things. What it does not do, unfortunately, is decrease the number of branches. There's still one branch at the bottom of that loop, and every iteration of the loop requires that branch to execute. Branches, as I've alluded to and we'll see in detail later, turn out to be the single most difficult part of implementing an instruction set in a pipeline processor. So in fact, all of these things have been decreased, but the number of branch operations as a percentage of all of the instructions has been increased. So it focuses even more attention on getting efficient branch instruction execution. Yeah.
So is there a trade-off that you could make at some point to start replicating code rather than branching?
Absolutely. And in fact, decreasing the total instruction count is not always the only way to make a program run faster. And you're referring to a kind of technique called loop unrolling, where rather than having one section of code in the body of the loop and you branch back to the beginning of it each time to re-execute it, you can in fact unfold the loop and make multiple copies of the body of that loop, and instead of branching back to the beginning, you just fall through them one after another, so reduce the number of branches. That's a technique that's been used for 25 years in optimizing compilers to reduce the effect of expensive branches. So in summary, what are the instruction set architecture features that are good to put in to make the optimizing compiler do its job best? Well, one of them is to try to be regular. Make all of the operations, the data types, and the addressing modes orthogonal, so that any register can work with any data type, and you can do any operation on any register. The compiler writer doesn't have to build in special cases that require only certain operations to operate on certain registers. Divides and multiplies are an example where lots of old instruction sets, or even current instruction sets, require that multiply and divide use only specific registers, in which case the compiler expression analyzer has to predict fairly far in advance where to allocate registers so that in order to do a divide, the result or the operands required for that divide wind up in the right registers. That's really a difficult thing to do. The other thing is provide primitives, not complex solutions. Lots of people have tried to build complex instruction sets, and we'll see the VAX as one example, with very complicated instructions that try to match some specific language feature. It generally doesn't work. There are limited cases where those features can be used. The languages change, the compilers change, and those instructions have limited utility. The other thing is make the trade-offs between alternatives simple. If you provide one efficient mechanism to do something, it makes the compiler writer's life easy. It also makes that particular mechanism turn out to be a very common case in the processor, so that, as we spoke about before, the important part of improving performance is finding a common case and spending a lot of time making it run really fast. Well, if you've only provided a simple, efficient mechanism to do something and the compiler always uses it, then you can afford to spend a lot of your time optimizing the execution of that feature, because you know it's going to have a big effect on performance. A couple of other things. Make sure that constants can be used everywhere, because constant propagation is an easy thing to do in compilers and is a big win. Provide enough registers to allow sophisticated register allocation schemes to work. That's something which makes a lot of sense for compilers. It turns out to be something which is more difficult for human programmers to do. So back in the days where most people were assembly language programmers, providing 32 registers was simply providing a headache. But providing 32 registers for the compiler writer gives him a great advantage in being able to automatically schedule the use of those registers. The other thing is that there's information which sometimes gets lost, that either the programmer or the compiler knows that there isn't a way to communicate to the processor. And if you can provide a way to do that, then you can give the processor some hints about efficient execution. One is to help the memory hierarchy. You know that going to memory may be an expensive operation. Well, provide a way in the instruction set for the compiler writer to say, in a while, I'm going to reference such and such memory location. If you've got nothing better to do, processor, why don't you start getting it now? And the processor can use that hint to fill in gaps in its instruction execution sequence and get a leg up on referencing that memory operand. But it requires special instructions to be able to communicate that information.
Is that a feature you see in a lot of microprocessors or processors today?
Say again?
Is that a feature that you see implemented in today's machines?
There are some machines that have information about, in particular for virtual memory accesses, to say that I'm about to access a particular memory location, make sure that all the address translation has been done, and then later on, you actually execute the instruction that references the operand located there. So yeah, that's something that is done. Another example of communicating hints is to communicate branch guesses. The compiler sometimes has a pretty good guess about which way a branch is going to go, and if somehow it could communicate that to the processor, it could make a better guess about which of the two paths to follow. In fact, it's often the case that the programmer has even more information than the compiler does about which way the branch is going to go. It's always been a disappointment to me that there aren't ways in most high-level languages for the programmer to specify this information. If I could say in writing a C program that this if test is testing an exceptional condition that will almost never occur, I could transmit that information to the compiler, which could in turn transmit it to the processor and get more efficient execution of the loop which contains that conditional. But there are very few high-level languages that allow that kind of pragma information to be transmitted. Any other questions? What I'd like to move on to now is a few case studies of instruction sets. I think it's very important to be familiar with several different general styles of instruction sets that are either popular or have been popular. And what we'll do is look at in detail three. We'll look at the DEX-VAX, which is arguably the world's most complicated popular instruction set. There certainly have been more complicated instruction sets, but none that has gotten to be that had the popularity of the VAX. And it's a kind of end of the era. I think we'll never again probably see an instruction set like that, although the pendulum may swing more in that direction. The other one we'll look at is the single most popular processor in the world, the Intel 8086 architecture, which is hard to characterize. It's not really a CISC, it's not really a RISC, it's a very, I said angular design, I was trying to be polite. It's a design which has been much influenced by the history of the processor and where it came from. And we'll see how that has happened. From an intellectual point of view, it's perhaps not the most attractive processor. On the other hand, there are about 150 million computers on the planet right now, and probably 80% of them are this processor. So it's not something you can afford to ignore. The third example that we'll look at in detail is an example of one of the standard modern RISC processors. In fact, we'll be looking at one which is a fictitious processor, but is very much a subset of a MIPS or a MIPS 2000-like machine. In addition, we'll look at some variations, and I'll go through some of the ways in which RISC processors have been elaborated and varied upon by people who are not satisfied with keeping it very simple. Okay, DEC-VAX. The DEC-VAX was introduced in the late 70s, 78, and it was designed by DEC, Digital Equipment Corporation, as an extension to the PDP-11. And the basic problem they were trying to solve is the fact that the PDP-11 had 16 bits of address, and they had run out. It simply wasn't enough. And VAX stands, in fact, for virtual address extension. That was the major problem they were trying to solve. In the meantime, they couldn't avoid the temptation to make it a superset of almost every other instruction set that was popular at the time, including the IBM 360-370. And a lot of the complex instructions in the VAX are direct knockoffs of complex instructions that existed in the, or exist in the 360, 370, 390 series. So like many architectures, and probably many that will be designed in the future, it had to be compatible with something that existed before. It had the same data types. Aside from the design of the instruction set, it also had the same data I/O bus, the Unibus, which people had built and sold lots of peripherals for and had to be supported. But they added high-speed peripheral buses that were unique to the VAX at the same time. Later on in the course, if we get around to the section of talking about I/O design for processors, we may talk about some of these buses and what they look like. If you remember last time I said that lots of old processors wind up running emulators to emulate old instruction sets because people have to run those programs. Well, in the DEC VAX, they took that a step further and, in fact, included directly as part of the instruction set architecture, if you will, or as part of the hardware, a way to emulate the old PDP-11, which, as you might imagine, made the machine more expensive and more complex than it would otherwise have been. But the non-PDP-11 part of the instruction set had a lot of nice things going for it. It was a very orthogonal instruction set. You could use any opcode with any operand. It had lots, not lots, but some high-level language constructs, in particular instructions that we'll see for doing procedure calls that were meant to very accurately map the high-level language constructs that were in use at the time. Had virtual memory built into it, which PDP-11 didn't. Had ways to do rapid context switching. It had the notion of a process control block, which contained all of the registers and all of the state information that the machine currently contained, so that you could switch one process to another in a very cost-efficient manner. First implementation was the VAX 11780. It was a successful architecture, made lots of money for DEC. There were follow-on implementations. The first version had an 8K memory cache, had a translation look-aside buffer, which we'll talk about later, a way to speed up virtual memory management. Like many machines in its era, the implementation technique chosen to use for this machine was microprogramming, a way of basically running an inner small machine with a very simple RISC-like instruction set that in fact interpreted the more complex instruction set that programmers and compilers actually generated instructions for. And in this case, it was a very wide word, 96-bit word internal microcode, and in fact had a writable section, so that if you weren't happy with the instructions that were implemented by this microcode, you could add your own instructions by adding a writable microcode to the microprogram. That was most often used for diagnostics and rather than for customers to expand the instruction set. VAX was a general register machine, which was one of the kinds of machines we talked about before. It had 16 32-bit registers. They chose, in fact, to use the same register set for both integer and floating point, which is one of the choices that we talked about. Avoids having to do moves when you do conversions from integer and floating point. The hardware, however, did assign special values to some of the registers. And in fact, the first and most important was the fact that the last register, register 15, was in fact a program counter. And I believe DEC has a patent on the concept of using one of the general purpose registers as a program counter. I don't know if other machines not from digital equipment have used that and what effect the patent has on that, but we do have that. In addition, there were other registers, like register 14 dedicated to the stack pointer, register 13 to a stack frame, which has to do with the ability to do procedure call operations, and register 12 as an argument list pointer, which were dedicated to special purposes in the hardware. This is not just a software convention, in fact. These registers are used for these special purposes by certain of the built-in instructions. Most of the other registers were fairly general purpose. However, some of the instructions were so complicated and took so long that it was important to allow interrupts to occur in the middle of the execution of those instructions. And if you take an interrupt in the middle of a complex instruction, you somehow have to be able to save all of the state information to be able to restart that instruction in the middle when the interrupt is over. Well, what they chose to do, rather than include that state information in some hidden variables as part of the process block, they in fact use register 0 to register 5. So if you execute one of these complex instructions, like polynomial evaluation, you can't use any of registers 0 through 5 because it's going to be in use during the execution of that instruction. Processor status included things other than those registers that represent the current state of the machine. Condition codes, we'll see in a second how its branches work, but it's a conventional condition code machine. And other information for interrupts, for supervisor versus user state, for PDP-11 emulation mode, and so forth. Also a flag that says, in fact, that the first part of an instruction has been done, so that when you take an interrupt, you can recognize that that instruction has been partially executed, or so that the processor can recognize that that instruction has been partially executed and use the state information in the registers when it continues them. It was a 32-bit addressing machine. They went up by a multiple of 2 compared to the PDP-11, and that lasted them for the lifetime of this architecture. Let's not talk about paging now.
Question.
Yeah.
Is the PDP-11 instructions different from the VAX instructions? And
Yeah.
it was just a sort of a processor that did 2 instruction sets? Or?
Yes, it was a processor that did 2 instruction sets. It differed very much. Now, some of the functionality of the PDP-11 instruction set got carried over. Like PDP-11 had auto-increment and auto-decrement register addressing modes, and the VAX does too. But they were encoded in different ways, and you couldn't mix PDP-11 and VAX instructions because they were different encoding. So it really was 2 machines in one. Data types. Well, anything your heart desires. It's the basic answer. Data types. Integers can be 1, 2, and 4 bytes. 8 and 16-byte integers were defined as part of the architecture, but not fully supported by all of the primitive instructions. Floating point could be single and double precision, 32-bit and 64-bit precision. And the format they chose was very much like what is now standardized as part of the IEEE 754 floating point, which is sign magnitude mantissa. I assume you've all seen how floating point numbers are represented. This is a traditional sign magnitude mantissa, single sign bit up at the front, and the mantissa bit down at the end of the word. An exponent, which is 8 bits wide and is excess 127 notation, and this elided, the removed, assumed implicit 1 bit, like IEEE 754, that gives you an extra bit as part of the mantissa. Since all floating point numbers are normalized, which means that the mantissa always has a 1 bit, there's no reason to store that 1 bit. So they were fairly advanced in their choice of floating point representation. Or you might say that the IEEE 754 folks recognized that the VAX convention was a good one and adopted something like it. Lots of other choices. Variable length bit fields up to 32 bits. So you could define an operand which was bits 7 through 17 of a particular memory word. Character strings up to 64K bytes, although the character strings didn't have an explicit length. Numeric strings, which is to say decimal data encoded with a separate ASCII byte for each decimal number. And there were 2 kinds of those, one with where the sign was encoded in the last digit of the number, and another one where the sign was a separate ASCII byte in the front of the digit. In addition, packed decimal, where each byte represented 2 decimal digits packed into 4-bit nibbles. And all of these data formats are supported by opcodes that allow you to do moves, adds, multiplies, divides, and conversions between the different forms. In some ways, it's a programmer's playground and a machine implementer's nightmare. With respect to big endian or little endian, they really had no choice. The PDP-11 was little endian, and the VAX had to be compatible in data types and was therefore little endian. Okay, now we get to the fun part. How do you encode a VAX instruction, and how big can it be? Remember, we're comparing this to RISC architectures which have fixed width 32-bit instructions? Well, it starts with an opcode. Life is simple there. But an opcode as a single byte is not enough. There are 300 plus instructions. So in fact, sometimes the opcode is 1 byte, sometimes the opcode is 2 bytes. You have to decode the first byte of the opcode before you can tell whether there's a second byte to the opcode. Following that can be 0 to 6 operand specifiers. An instruction might have as many as 6 operands. The opcode itself implies the data type, whether it's a byte or a word or a string or a floating point number or a decimal ASCII encoded integer, and the size and the number of operands. So they have forms for both 3 operand instructions like A equals B plus C and 2 operand instructions like A equals A plus B. You get your choice. The operand specifiers include within them the addressing modes. So any one of these operands, where it makes sense, can be any of the addressing modes that we'll see, of which there are many. And in some ways it's very nice, because any opcode can appear with any operand of any mode as long as it makes sense, as long as it is unambiguous and is interpretable. So let's look at what one of these operand specifiers might look like. It can be as short as a single byte. The first 4 bits of the operand specifier is a mode. Well, almost the first 4 bits. Mostly the first 4 bits are a mode saying what kind of operand addressing you're using. In fact, they recognize that literals or immediates are so important that they wanted to allow short literals with very small encoding. So if the first 2 mode bits, or rather if the mode began with 00, then the other 6 bits represented a literal or immediate instruction. But in fact, depending on the opcode, this immediate could be several different types. It could be an integer, in which case it's a positive integer from 0 to 63. It could even be a small floating point number. And if the opcode implied that this operand needed to be floating point, then those 6 bits were interpreted as a 3-bit exponent and a 3-bit fraction. And it's very clever. They chose the encoding so that, in fact, that floating point representation can encode all integers from 1 to 16, all 16ths from 1/16 to 15/16, plus a selection of a few more constants. Unfortunately, as we'll see, I think, those constants are not often the constants that are popular in floating point programs. So it was clever, but not necessarily a great win. If it's not a literal, then in fact there are 4 bits that completely specify the mode, and you get things like register, register deferred, optional auto increment and decrement. I guess I don't have anything that describes them in detail, but basically it's the list we went over last time. That was pretty much taken from the backs. You get to choose displacements from a register of 1, 2, and 4 bytes in size. You can optionally defer them or make them go indirect through memory. There is a scaled mode that allows you to take a register, multiply it by the operand size, and then use the next operand specifier for the remainder of the effective address calculation. Now, one of the things they did is, in fact, not include, except for this literal format, short literal format, any specific encoding for immediates. Because it turns out using the PC as a general register with an auto increment mode gives you a free way of getting immediates encoded within the instruction. And let's go over an example that shows how that works and why they must have been very proud of themselves. Let's take an instruction like add. Let's say that we're going to add long 3 operands. We want the result to go into register 1. We want the first operand to be taken from memory location, which is specified as 100 bytes past wherever register 2 is currently pointing. And we want the third operand to be a constant of 200 decimal. How would this instruction be encoded? Well, single byte opcode. Turns out that add is popular enough, so they recognize that this form of add ought to be a single opcode, and in fact that turns out to be C1 in hexadecimal. Now we need to specify the first operand, which is R1. Well, we can do that in a single byte. We're doing well. The first 4 bits is the indicator that means that it's register, and then a 1 to indicate register 1. Now we need to do the displacement addressing, and in fact this can be done in 2 bytes. A single byte type that says that it is in fact a byte displacement mode, and the register number, and the encoding in a single byte of the displacement. Now here's where things get interesting. After these instructions have been interpreted, the program counter for the machine is pointing here, because as it's interpreting these instructions, it advances after the interpretation of each operand specifier, the program counter. It looks at this mode specifier, and in fact this is the mode specifier that says that it's an auto increment type reference. It means that I want to take the contents of register R to be the address of the memory location to reference, and after I'm done, increment it. And the register I want to use is register F, or 15, which just happens to be the PC. So after this mode specifier has been fetched and interpreted, the PC has been incremented past it, and in fact points there. So this specifies that the memory location from which to fetch this operand is the current location of the PC, and it's a word long because the opcode said that it was a word long. So in fact these 4 bytes as part of the instruction are fetched as the memory operand, and encoded here is 200, C8000000. Auto increment on this machine works such that after the value has been fetched at that location pointed to by the register, it increments the register by the size of the thing which has been fetched. So the PC then points past the end of the instruction. Very clever way without any extra encoding to get immediate fields in the instruction to be handled no differently than an ordinary auto increment register mode. Very clever. It makes efficient and high-performance implementations very difficult because it's an interpretive process. As you interpret the bytes of this instruction, the program counter gradually marches ahead, and you don't know until you've interpreted the last byte of the address specifier for the last operand where the next instruction is going to begin. So if you're trying to make a processor that gets going on the execution of multiple instructions at the same time, you've got a challenge in this architecture. Any questions about that? Okay, a couple, quickly go over some of the highlights. It has the collection of integer and floating point instructions that you might imagine, moves, simple arithmetic operations, and so forth. Has a bunch of bizarre operations or complex operations like polynomial evaluation for floating points, modularization, a way to reduce the range of an operand, like for sines and cosines, into a manageable range. Strings allow you to move simply by specifying a length and a source and a destination, or you can specify a source length and a source, and a destination length and a destination, and if the lengths aren't the same, then you specify the character to fill. Some of these you might recognize as C-like constructs, or even Pascal-like string constructs, and in fact they were designed to be directly useful for those higher level operations.
I have a question.
Yeah.
Okay. Increment.
Yeah.
If you increment by 1, actually, I mean, should you increment by 4 instead of 1?
The PC is incremented by 4. At the point that when the PC is sitting over here and it's about to do the register auto increment, it fetches the word pointed to by the register, which is PC, and then it increments the PC by 4. And it does that automatically. That's the way auto increment addressing mode works. It increments by 1, 2, or 4 depending on the length of the thing that it just fetched. Right. So it does increment by 4. All sorts of wonderful string instructions. You can move translated. You specify a table which indicates how characters are to be translated. You can do that based on a length. You can do that based on or until a particular character is matched. There are a whole section of string operations that are C-like string library functions to skip over characters, to look for occurrences of characters, to locate substrings. These are the kinds of complex instructions that take a potentially unbounded amount of time to run, and in fact use registers 0 to 5 to maintain their state information so they can be interrupted. Lots of decimal arithmetic operations. A bizarre kind, I don't think I put it on this list. No, I did. I put it on the next list of bizarre operations. This was stolen directly from the IBM 360, 370 series, which is a, COBOL people love this. It's a way of taking a packed decimal number and converting it to a character string using what amounts to a little program, interpretive program, written as a special pattern with opcodes in it. So you can take a packed decimal number and create things with dollar signs and decimal points and leading minus signs, with or without leading zeros, pluses, minuses. It's basically a mini programming language. But in fact, it's a single instruction that the implementer of this instruction set has to somehow get the hardware to execute. What are other wonderful things? Find first bit. An instruction beloved of people who do disk allocation routines, because if you're doing disk allocation and use bitmaps to represent used blocks on the disk, one of the operations which you can't do without a loop in most assembly language instruction sets is finding the first on bit in a word or a string. So they provided an instruction to do that for you. Instructions that directly manipulate queues so that you can insert and remove in a queue. Instructions to do subscript operations like the scaled addressing mode we saw, but in addition to check against subscript bounds and to trap if the subscript was out of bounds. And on and on. Lots of wonderful to use, fun to use instructions, but hard to implement, hard to make efficient. Branches are more conventional. It's a conventional condition code machine. There's a global status register containing condition codes. Most of the moves, most of the ALU ops set them. Conditional branches test the condition code and branch, but only within 128 bytes of the PC. And in fact, if you need to branch farther than that, you wind up doing a conditional branch, let's say around an instruction which is a long jump to the place you really wanted to go to. You negate the condition. If it's not true, you jump around, and if it is true, then the jump goes to the location you really wanted to get to. We saw some of the statistics. 128 bytes from the PC probably covers a lot of the cases, probably not enough of the cases. They have PC relative jumps as well as absolute jumps. They have loop instructions that do essentially the do loop or the for loop construct in a single instruction. Add to a register, compare to an ending value, and branch. The procedure call instructions were ones that really got out of hand in the sense of trying to perfectly match the languages that they expected people to be writing in and to implement all of the procedure entry and exit. And just for your amusement, here's a list of some of the operations that a VAX procedure call might have to do. Well, it aligns the stack because the stack might not be in a word boundary, and for this purpose it has to be on a word boundary. It pushes the argument count. One of the things you specify in the call instruction is how many arguments you're passing. It saves registers automatically, and in fact it does this in a very clever way. You do a call instruction to a procedure P. In fact, the first word of procedure P is not an instruction at all. The first word of procedure P is a mask that contains, among other things, an indicator of what registers that procedure is going to be using. So the call instruction fetches that first word, saves on the stack only those registers that called procedure is going to be using, and then it starts fetching instructions. Now, actually, this is not a bad scheme in a lot of ways. The caller is saving registers. The callee, the called procedure, specifies which registers are to be saved because, in fact, it's the only one that knows what registers are going to be destroyed. So the caller doesn't wind up saving registers that the callee, the called procedure, doesn't use. Pushes the return address on the stack, manipulates the stack frame pointer, tries to do automatic procedure call entry, allocation of local variables, so it keeps not only a stack pointer but a frame pointer. How many of you have seen how this works in high-level languages, the use of frame pointers and stack allocation? Is that something you know about? Sounds like most of you do. In any case, it's not something that's required for this course. If you recognize what these things are, you understand how they're used, and in fact, in most modern processors, they're simply done in software, either in the caller or the callee, but in the VAX, it was all built into the instruction set. They really tried to make the VAX as much as possible a high-level language processor.
Question?
Yeah.
I'm a little confused about the entry mask because it seems like procedure P could call somebody else, who could call somebody else, who could call somebody else. So does it have to check every potential call that might come out of there?
No, it just checks the mask for P, and mask for P indicates what registers P is going to destroy. If P calls Q, Q has its own entry mask. So
right,
when P calls Q, then that call instruction will save Q's registers on the stack. And in fact, they may be the same registers that P saved. You look confused. Okay. Clears the condition codes, push the status, including the saved low bits of the SP. It aligned the stack on a word boundary, but when it exits, it's got to put the stack back to the way it was. So in the meantime, it has to save and then later restore the low 2 bits of the stack pointer. One of the things that the mask specifies is how overflows are to be handled in this procedure. You may be calling a procedure that either does or doesn't want to handle overflows for arithmetic operations. So the overflow trap enable is set depending on what's specified in the stack, in the mask for that procedure. Finally, it updates the stack pointer and does the jump. And then, of course, the return instruction has to do exactly the opposite, undoing all of this operation and returning to the core.
Is the information as far as like whether you align the stack or not and what the mask was, is that put on the stack for the return?
No, the low order 2 bits of the SP are always saved there, whether or not it had to do the alignment. So if it was already aligned, then it does nothing and saves 0, 0 as those saved bits. And the mask was always used. Every procedure began with a mask, and the mask bits might be all 0, saying you don't save any instructions, don't save any registers on entry, but it still had to look at them and then look at them on the way back to be able to undo the operation. The mask itself got saved on the stack frame so that it could undo that operation on the return.
So can stack point to a byte address instead of word address?
Yes, the stack could point to a byte address.
Then the virtual memory of 32-bit is, so it's not really 32 words. I mean 32 bits of words.
No, the VAX had 32-bit addressing, and it was to the byte level.
Bytes
so
level.
There were 2 to the 32 bytes that it could address, or 2 to the 30th word. That turns out to be common even in machines that are much more word-oriented. Like the RISC processors that we'll see, they, for example, require the stack and operands and all sorts of things to be aligned on word boundaries. Nevertheless, the address is the address of a byte. And when you go from one word to the next word, you increment the address by 4, not by 1. We'll see that in more detail. Byte addressing these days is the norm. There's hardly a machine ever designed that doesn't have byte addressing. Whether or not the stack and operands are required to be on specific boundaries varies from machine to machine. Now, just before we leave the VAX, I wanted to point out that it could be worse. There have been proposals and sometimes even implementations of machines that have even more exotic architectures and even more bizarre instructions than the VAX. And in particular, in the 60s and 70s, the literature was filled with people that were proposing very complex instructions to do all sorts of things. For about 5 years, capability-based machines were very popular. It's kind of a primitive object-oriented programming built into the machine itself. The capability is an object. It's a thing which confers a right. Your right to be able to access an operand, to read a variable or to write its value. And in fact, this was a very complicated protection-like machine where you specified protection as a matrix of capabilities based on what capability you had and what object you were trying to reference. And capability was a thing sort of like an encryption key that allowed you to get access to something, and you could pass that capability to somebody else, but in fact it had an unforgeable name. You couldn't make a synonym of that capability and pass it to somebody who didn't have the right to have it. This goes way beyond putting high-level language support into the machine instruction design. This is putting operating system support into the machine instruction design. But there were machines that were proposed and designed to do that. There were lots of other machines that followed along that line, sometimes earlier in time, with putting into the instruction set design a lot of operating system functions, like protection domains, and allowing you to write mutually suspicious cooperating processes in a way that the hardware did all of the checking rather than the software. There were machines that directly interpreted high-level language. Fairchild symbol machine was one. There were other proposals, I'm not sure they were built, for machines that directly implemented Fortran. There were certainly machines built that tried to directly implement Lisp and other high-level languages. There was a fad for a long time of addressing that went down to the bit level rather than the byte level. It relates to the question you were just asking about whether the address specifies a byte or specifies a word. Almost always it specifies a byte now. It used to specify a word. People saw that transition and said, well, if word was good and byte is better, then bit is even more better than that. So in fact, there were machines like the Burroughs B1700 that had variable word length. You could define the size of a word to be anything you want. You could make a 37-bit integer. And in fact, you address that word by specifying the address of the first bit of that word. Needless to say, it was a terror to try to design an implementation of that machine that was efficient. It's fun to look at the description of these machines. A lot of them, in fact, if you look at them now as descriptions not of instruction set architectures, but of environments in which programs are to be run, are not so strange. A lot of this protection work and the segmentation work winds up being done now in software and operating systems, but it's been taken out of the instruction set design. And rightfully so, if we're interested in getting high-performance processors. I think we better stop here for today. Tomorrow, or next time, we will go over the Intel 8086 series and the RISC series.